your homework 6 towards the aisle that was closest to you, and I'll pick them up. Hey, we have a test on Monday. Ah, yeah, that's great. Alright, so I'm trying my best not to make this a big problem that so many people are not here, which is part of the reason why we're doing the video recording again. I'm not entirely sure how helpful that is, but depending on what they can see and so on. But of course, we also have the audio recording video where we're going to do it. Oh, you go that way, okay, great. So anyway, all these materials will be available to you. Now, if you've been following your email or whatever, however you get the messages on Blue Line 2 today, you saw I also posted a giant list of everything that you have associated with this unit of the course. So, for example, it has links to the course outline, it has links to all the keys from everything we've done so far this unit, like all the homeworks and so on. It has, the only thing I forgot, links to all the Blue Line, the PowerPoints and so on. I did forget to put a link to that anatomy of the general circulation handout. I can add that if somebody reminds me or whatever, otherwise, hey, I would guess by now you have that. But if you don't, there would be. So anyway, you got an email message with all that stuff, as well as, how to contact me over the weekend and so on, since we don't have office hours on like Friday afternoon. On the other hand, there's lots of office hours between Monday morning and when we take the test, so that'll be good for you too, okay? So you have lots of ways to get a hold of me. There's, get this afternoon, there's lots of hours at the help desk, although I'm a little bit skeptical they're going to show up today with the game going on and stuff like that. So anyway, you have lots of stuff. Now, this is an important unit. This is kind of the big lecture. This is the big picture lecture, in which we put together what all we have done in this unit and figured out how, we learned about the general circulation, but no particular day looks exactly like the general circulation of the atmosphere. And then we start picking it apart and seeing, well, gee, this is actually what it looks like day to day. This is how the general circulation manifests itself in terms of like air masses and cyclones and so on in our part of the world. We also briefly talked about El Nino in this unit of the course. Make sure you get like the review sheet and so on, which will have good guidance as to how to prepare for the test. Alright, so, in this unit, we were talking about, fundamentally, what are these rules of the atmosphere resulting in? All this physical law stuff that we did in the first 2 units of the course. Radiation, conduction, convection, all these forces and so on. Now we're starting to break it down and saying, how does that actually manifest itself in terms of fundamentally how the atmosphere works? And our first start here was this business of how Sir George Hadley thought it was going to work, like 400 years ago or something crazy like that. And it's not a bad first guess. Hold on just a second. Anyway, okay, so I just missed the first couple of announcements at the beginning of class and so on recording. But that's okay, we have the video recording. Alright, this is not a bad first guess. Sir George Hadley did not know a lot of important things about how the atmosphere works. For example, Sir George Hadley he did know things like warm air in the tropics should be rising, and he did know that cold air in the polar region should be sinking. He didn't know about the tropopause, but he had some idea that it had to be like a top to the atmosphere. So the air didn't just keep rising and rising and rising out into outer space or something like that. He had some idea that there must be these circulation cells. And it's not a bad first guess. It is a bad first guess, but it's not a bad first guess when you think about the fact that he was born in like the 1500s. Okay, didn't know about Coriolis force, stuff like that. Instead, we need a much more complicated idea of what the general circulation looks like. And this is how we built this sort of 3-cell circulation model, where there are 3 cells in the northern hemisphere and 3 cells in the southern hemisphere, one of which works a lot the way Hadley thought. Hence we call it the Hadley cell, where there's rising motion at the tropics. Now, Hadley had no way of knowing about adiabatic processes and stuff, the kind of things that you learned about in the second unit of the course. He had no way of knowing that rising air in the tropics should be causing thunderstorms. That's the ITCZ, the Intertropical Convergence Zone. He had no way of knowing that rising motion was going to be causing that. But we know that now. And there should be this band of thunderstorms that more or less spans the tropics, Intertropical Convergence Zone. We're going to see how it's a region of convergence of the trade winds. That air rises and it hits the tropopause and starts spreading to the north and spreads down. It becomes our first example, by the way, of some place where there is low-level convergence, rising motion, and upper-level divergence. And you get this little circulation cell. Upper-level winds spread out towards the north, spread out towards the south. They get deflected by the Coriolis force, which is not very well illustrated on here, to set up the subtropical jet stream. At some point, at 30 degrees north, they're going to start sinking. Sinking motion is associated with high pressure at the surface. It's associated with dry conditions. All clouds form at a rising motion. Sinking motion means they're very dry conditions. Well, that's around 30 degrees north, 30 degrees south. That's where all the world's great deserts are. The Sahara, the Gobi, the Kalahari, the Atacama, the Outback. All these places are about 30 degrees north, 30 degrees south, because they're more or less permanently under these areas of sinking motion, the subtropical highs. They're areas of high pressure, so they have anticyclonic rotation around them. In the northern hemisphere, that's clockwise. In the southern hemisphere, that's counterclockwise, which means on the equatorward side of these subtropical highs, you get these winds that are kind of coming out of the east, northeast, something like this. They call those the trade winds. Now, this is at the surface. You have these trade winds at the surface. The word trade, it didn't mean what you thought it meant. The word trade ended up meaning persistent. It's a very old, strange word. It's the same stem from which we get the word tradition. And though trade winds are altogether different than the kind of winds that we see in our part of the world, these winds are remarkably persistent. In one of my other classes, we actually bring up data from like ocean buoys that have wind measuring equipment on board, and you could actually see how ridiculously, the wind will be very steady in the same direction at almost the same speed for days and days and days. That is just not the way it works in Omaha, right? The wind blows from a different direction, hour by hour, right? We do not have the trade winds in our part of the world. You can see we have northeast trade winds in the northern hemisphere, they have southeast trade winds in the southern hemisphere, and they kind of converge near the ITCZ. This particular printing of the book got hung up on this word equatorial low. I can honestly say I've never heard the word equatorial low except in that one book. Okay? Rather, a better way to think about this is that this is the area called the doldrums underneath the ITCZ. The doldrums is this area right under the ITCZ itself where all that convergence is happening, and the winds there happen to be kind of weak. You might remember the stories that we told about, like a ship, a sailing vessel that gets underneath the ITCZ gets stuck in the doldrums, where there's very little wind to push them out of the way. That's in contrast to the horse latitudes, which was that area of weak winds right around 30 degrees north, right in the middle of the subtropical highs. Those are those areas where a sailing vessel also gets stuck, but it would be stuck there because of the, it's stuck there because of weak winds, but then it's also in an area of sinking motion, so there is very little rain, and it's a problem if you're a horse on board a ship because they're going to eat you rather than let you drink all the water. Anyway, but we told that story in much better detail the other day in class. Hadley cell. Not quite what he was picturing, but not a bad guess. Up there at the polar regions. Well, Hadley was right. The cold air that's being processed up there at the North Pole is going to be sinking. It's cold, it's dense, it's going to be sinking. And you're going to end up setting up a polar cell, where you have high pressure and sinking motions near the pole. Air is going to spread out to the north, spread out to the south, upper low-level divergence. It's eventually going to encounter this warm air coming from the south and have rising motions along the polar front. And we're going to have this polar cell. And hey, in between here, we're going to have this other cell where we have sinking motions near the subtropical highs, rising motions up near the polar front, and so on. And you get this kind of cool. I happened to catch this animation this morning. I was playing with Google's new search for animated GIFs tool. And it's not so great, but I like this little animation here to kind of illustrate the three circulation cells in cross-section here, where they're showing, you can see that there's rising motion near the equator, sinking motion around 30 degrees north, rising motion up around 45 degrees north, roughly where we are, where the polar front is, and sinking motion up near the poles. This is not the world's greatest animation, but it kind of gives you a way of thinking about that if you haven't been able to envision these three circulation cells before this. This polar front turned out to be basically the part of the world where we are. See how it's kind of like a girdle or a belt or a necklace or something that goes all the way around the world at about 45 degrees north-ish. All right? It's the boundary between the cold air coming off these polar easterlies and the polar highs and these warm air coming off these subtropical highs at the surface. There's this boundary. That boundary is going to move from day to day. It's not just out of a line the way it's drawn right there. This is going to become cold fronts, warm fronts, stationary fronts, and that whole popular story. But we're not quite there yet. But you can already see that if this is able to move, you can see how in our part of the world the weather becomes so variable. You can see how there will be days when we're on the cold side of the front and we're getting air masses from a very, very different place than when we're on the warm side of the front. Which is why our weather is so variable. We don't have weather very much like the polar easterlies, where it is cold and dry all the time. Remember, the polar regions are like incredible deserts. I know Santa lives in the land of snow and ice, and on that one foggy Christmas Eve, Santa came to say, but you know what? There's no fog. It's cold and dry there. Sinking motions, they get like an inch of snow per year in Antarctica at the South Pole, okay? front, on the other hand, is a very variable place. Depending on exactly whether you're on the north side or the south side of the front, you're either going to be in warm southerly winds, or you're going to be on cold northerly winds out of the north. Remember, we always describe winds in terms of where they're coming from. A north wind is from the north, a south wind is from the south, a sea breeze is from the ocean. All that kind of stuff. These are just kind of giving you a sense of what, again, this is just the surface winds at that location. See trade winds, westerly, subpolar highs, polar highs, etc. Now, in real life, they're a little more complicated than this, as we got talking about when we talked about El Nino. Notice how all of our discussion that we had about general circulation, we didn't worry about like from one longitude to another. We assumed that whatever was going on at this longitude is also what's happening here and here and here. It's all a subtropical high, or it's all trade winds at this latitude. Well, in reality, there's some variation from place to place, depending on like the arrangements of continents and water temperatures and stuff like that. But the idealized picture, like what's on the left, is all you have to know in this class. Now, this has all been surface stuff. We haven't gotten too far yet on jet streams and stuff like that. Okay, everything we've been talking about so far is surface stuff. Hey, remember that business of the warm air rising near the equator and how that gave rise to the ITCZ? Well, that ended up being associated with monsoons. Remember, monsoons were about this business of how that ITCZ is going to shift from north to south over the course of the year. In fact, if I actually pull up, again, I was playing with animated GIFs today, and I found this nifty thing. Here's the general circulation over the course of a year. See how the ITCZ, which is this red dotted line here, see how the trade winds are converging, and this is the ITCZ, see how it's the rising motion here? Over the course of the year, the ITCZ is going to move north and south. In the northern summer, it's going to move north of the equator. In southern summer, it's going to move south of the equator. And this whole multi-cell circulation system moves with it. Well, if you're at a location like, say, here, notice how part of the year, right now, you're under the wet part of the ITCZ. See the ITCZ right here? But later, at that part of the year, you're under the subtropical highs. See how the subtropical highs here with their with their clockwise rotation? I wish the sleep could slow down a little bit. So like this location here, where they have labeled by a star. See how the ITCZ is on top of it with the red line here, and then the subtropical high is on top of it with the blue line? They're going to have a wet season and a dry season. That's a monsoon climate. Lots of places down near the equator have a monsoon. Where in their summer season, they're under the ITCZ, and they have a very wet climate. And in the winter season, they're under the subtropical highs, and they have a very dry climate. That's just sort of the annual march of these features here. I thought that was actually pretty cool. I found using that one in a different class. We had 2 jet streams in each hemisphere. All of the jet streams that we learned about in this class are like rivers of, oh, I hate that analogy, that they're like rivers of air. But I kind of get it. If you're first beginning to learn about jet streams, that's not a bad idea. The idea that there's like these channels in which there's air flowing much more rapidly from west to east than there are in other places. They're all in the upper troposphere, just below the tropopause. There were 2 in the northern hemisphere, 2 in the southern hemisphere, and all the ones that we learned about in this class come from the west. 2 of them were not really all that hard to explain. 2 of them, the subtropical jet stream in the northern hemisphere and the subtropical jet stream in the southern hemisphere, not illustrated here, maybe down here someplace, are pretty straightforward things. Basically, air rose near the equator in terms of the ITCZ, in the updrafts of the ITCZ, headed out towards the north, or towards the south down in the southern hemisphere, and got deflected by the Coriolis force that becomes a subtropical jet stream. It's not terrible. How to explain why it gets so damn fast, that's a very complicated story. But the general nature of where that air is coming from, not terribly complex to understand. Mid-latitude jet stream turned out to be a big mess. Okay? The mid-latitude jet stream was altogether a more complicated story, because that was that whole business of the thermal wind relationship. Oh my gosh, thermal wind relationship. I really hope Dr. Stragi doesn't put that on the test. What are you thinking? Of course it'll be on the test. We spent like 40 minutes on it. Okay? It will, of course, be on the test. On the other hand, obviously there are a range of questions about it. Relatively easy questions about identifying ways in which it works, and then much more complicated, like applications of it and so on. What's the core nugget to know about the thermal wind relationship? The basic 0th order thing to know is what the thermal relationship means. It tells us that at the surface, when you have a big temperature gradient, a place where the temperature is changing from cold air on one side and warm air on the other, then you have a jet stream above there. So like if you have a cold front, a warm front, a stationary front, that is to say any kind of polar front, at the surface, above there at the tropopause, or just below the tropopause, you're going to have this jet stream. That's the thermal wind relationship. Well, that's one application of the thermal wind relationship. The whole story about the thermal wind relationship and how it's about changes in thickness between the cold side and the warm side, which leads to changes in pressure gradient aloft, which causes big pressure gradient force from the warm side to the cold side. But then because these are in geostrophic balance, therefore if we have a big pressure gradient force one way, you got to have a big Coriolis force the opposite way. How do you get that big Coriolis force? By having a big wind that direction? Oh my gosh, big complicated story. All right? It would take me like another 40 minutes to tell that whole story in detail again, right? So we're not going to do that right now. That's why we record those lectures and so on. And if you want, we have other times that we have like a narrated PowerPoint. If you want it, just let me know. I'll send it. Whatever. We have the whole story. The big take-home message, though, is right above that polar front, you have a mid-latitude jet stream. In both the northern hemisphere and the southern hemisphere, it's a westerly wind. I really wish we had time in the intro to go into more detail as to how the mid-latitude jet stream and subtropical jet stream work, because it's much more cool. It's much more cool. It's much cooler than just sort of a river of air. Okay? I mean, no, it's all going from the west to the east and that. It's a channel where they're going faster. Think of it as a river. It doesn't really work because you know what? When you get to the edge of the river, you're on land and it isn't moving. Okay? It's more like a current, you know, where the water's all going the same direction, but one part might be faster. And it's much cooler than just sort of being like a river. They actually kind of spiral like a football as they go. As they, you know, like the flow is twisting as it goes. It's very cool in 3 dimensions how they work. You can't do that in this class. Not because it's just like the materials aren't in the book and so on. So instead we populate our understanding with that stuff about El Nino. Remember we had that little block of material about El Nino this semester, where we talked about how this idea of the general circulation is the mean way in which the atmosphere is working. But it can change. There can be year-to-year variability. There has to be a reason why this winter's, especially March, has sucked. Whereas last year, by this time, we had 3 days in the 90s already. I know, that sucked too. There has to be a reason why we have interannual variability. If the atmosphere just sort of works this way every day, why do we have one year that's different from another? Well, the primary example of a way in which the years vary from one another is El Nino. Remember, El Nino was this story about how you can get changes in the trade winds, especially across the Pacific. Across the Pacific Ocean, you got these trade winds pushing from east to west every day of the year. Years and years and years. And as they do, they push water across the tropical Pacific from South America off towards Australia, resulting in water. By the time it gets to Australia, it's ridiculously warm. Warmer than, it's like bath water. Why? Because it's been basically at the equator where the days are long and the sun angles are high for like a year or more as it's been pushed by these winds across the equator. And it makes this big pile of warm water out towards Australia, New Guinea, and so on. Why is it a pile? Those winds, those trade winds, they're so persistent, are pushing on that water across the surface, and they're so persistent, and they're spread over an area the size of tens of thousands of millions of kilometers, that they're exerting enough force that that pile of water in the Western Pacific is physically higher than the Eastern Pacific. Not a ton, we're talking like a half a meter or something like that. But that's a whole lot of energy that it would cause to hold up a pile of water like a half a meter taller on that side of the ocean than on this side of the ocean. The ocean's not flat. Sailing from South America to Australia is uphill. Not just a ton, like a half a meter, but enough. There's a whole lot of energy involved. And if you ever have a weakening of those trade winds, if they ever, for some reason we're getting a little weaker, you're not going to be able to hold that pile back anymore. It's going to come sloshing back towards South America. And you're going to get an El Nino event, where you get this warm water out over the coastline of South America and Central America, and it sets in pattern all kinds of changes in the world's general circulation. Because suddenly you have warm water, which has different fluxes of heat from the surface by conduction and so on, just to tie it back to the first unit, and different rates of evaporation, just to tie it back to the second unit, which starts changing the general circulation. And starts screwing with the weather. We get these weird weather patterns where jet streams aren't where they're not supposed to be, and you get weird areas of drought, and weird areas of rain, and so on. This happens about every 4 years on average. About every 4 years, we hit an El Nino pattern, where, for reasons that are complicated and not entirely understood, we get this weakening of the trade winds, warm water from the Western Pacific moves over to the Eastern Pacific, and it screws with the general circulation, and it lasts about a year. and then conditions go back towards normal, maybe even stronger trade winds than normal, which was called a La Nina, where you got even higher than normal water temperatures out in Australia, etc. Just sort of an example of how we can mess with the general circulation. Well, let's go back. El Nino is far away from here. Let's get closer to where we live. Air masses. Hey, what's going on here? The link isn't working. Oh well. Air masses is one of the topics that students love in this unit. Not because it's necessarily easy, but because it's more of their comfort zone. Gee, there was a PowerPoint with bulleted lists, definitions. Oh my goodness. You can say that. Get those questions right. Okay? They're going to be a lot like the questions on homework 5, where you had like a list of air masses, and then there were questions that said, which one of these air masses does this, which one does that. What are air masses? You can think of them as parts of the subtropical highs and the polar highs that have broken off. That's not exactly right. Someone on YouTube is going to comment on that when I post this up here. But, because somebody always comments on stuff they put up here. I don't know who these people are who sit around watching this lecture from someplace else, but they're here. And they are going to be saying that that's not entirely right. That's true. It's not entirely right. That's not a bad way to think about it. Because their air masses are areas of high pressure that come from up by the polar high, or they come from down by the subtropical highs, but they are high pressure, and they are large. They cover an area like multiple states, and they have roughly homogeneous properties throughout. That doesn't mean it's exactly the same temperature in every location or exactly the same humidity, but the difference between one air mass and the next is bigger than the difference between, like, inside of the air mass, okay? So, if we're under some cold air mass right now, maybe the temperature's in the 20s and the 30s throughout, and if you get on the other side of the cold front from here, down farther to the south, like in Oklahoma or something right now, maybe the temperatures are in the 60s and the 70s or something, okay? So, there's a bigger difference between air masses than inside the air masses. Air masses are labeled based on where they came from. Not like specifically, oh, this is a Gulf of Mexico air mass, or this is a North Pacific air mass, as so much as in what the properties of it were like. Was it maritime or was it continental, an M or a C? And was it, yes, maritime or continental, and was it tropical, or was it polar, or was it Arctic? That's confusing. The original acronyms actually come from Norwegian, if I believe correctly, and they just sort of squeezed these terms to work in so that the letters still worked out. Because polar would seem like it comes from the pole, but polar just means kind of cool. Like it came from Canada, or it came from the North Pacific, or the North Atlantic. Arctic means it actually came from like up by the poles. Very, very cold air mass. Yeah, they're squeezing these terms to make them work. So you had, well, it seems like 6 possible types of air mass: maritime polar, maritime continental, maritime Arctic, continental. One of those didn't exist. Maritime Arctic didn't exist. Remember, because you would have to have a very cold but very moist place. Well, any place that's very cold isn't going to be very moist because it's not just going to be frozen. Okay, so that doesn't exist. But the other 5 all did, and then we had a little PowerPoint where we talked about all the different types of air masses, and you had readings in the textbook that talked about all the air masses and so on. Get those questions right. Which one is most humid? Going to have the highest dew point would be a more accurate way to do it. Well, but that would be the maritime tropical ones, right? Warm air holds more moisture, and it's maritime, so it actually came from a moist place. It's going to be the most humid. Which one of these is going to tend to be coldest in the winter? Well, it's going to be the continental Arctic ones, the ones that come from a very cold, dry place. If they came from a place that was wet, I mean, how cold can it be? If there's open ocean water or whatever, like the North Pacific, I mean, it can't be colder than 32 degrees because it wouldn't be open ocean water anymore if it was that. Which ones come from the deserts, regions of northern Mexico? That'd be continental, tropical. You know, those questions sound familiar. They're the kinds of things you did on homework 5. Get them right. You need the points. That sounds bad. You're going to need the points. Because then you're going to get to fronts. Oh man, that fronts lecture this time bummed me out. It fell on the Friday before spring break. Everybody skipped. No, that's not true. About half the people were here. Fewer than were today. I'm actually quite proud by how many people eventually did come. But you know what? On that Friday before spring break, we did video record the lecture. If you weren't here, you can watch it all in all its glory. Which sounds like torture to me, but hey. Okay. But you can learn all about fronts. We learned that there were 5 types of fronts: cold fronts, warm fronts, stationary fronts, dry lines, and occluded fronts. And 3 of them were types of polar front. Thinking back to our idea of a polar front again. Polar front, meaning that there's cold air on one side and warm air on the other. Those were cold front, warm front, and stationary front. All of them were cold on one side, warm on the other. Cold air from the north, warm air from the south was meeting along the polar front. In that case, cold front, warm front, or stationary front. And really the only difference is which was pushing the other air mass out of the way. If the cold air is advancing, that's a cold front. If the warm air is advancing, it's a warm front. If neither one is able to push the other one out of the way, it's a stationary front. Gee, that's not hard. You know what else is kind of fun about those cold fronts? We have questions in there about things like how are they drawn. Cold fronts are a blue line with a blue triangular teeth pointing the way the cold air is moving. Warm fronts are a red line with red semicircles pointing the way the warm air is right. Okay, you know what? Those are really easy questions. Get them right. Okay. You know what? There's other simple questions that just come from the basic nature of cold fronts, warm fronts, and stationary fronts. Which one is more steeply sloped? The cold fronts are. Which ones move faster? The cold fronts do. Which ones have overrunning along them? The warm front. Just get all those questions right, okay? There's plenty of hard questions on this test. Get the easy ones right. That's good advice in general on tests. Get the easy questions right. Because there's plenty of hard questions coming up, right? How these things, I mean, this identification of basic properties of the fronts, I mean, you know, you can watch the video, you can read the book, you can do whatever, you can have Ben at the lecture, God forbid, and you would know all that stuff. And that's going to be a relatively straightforward set. But then you start getting into this business of their whole role in the life cycle of mid-latitude cyclones. Because mid-latitude cyclones are going to be developing along the polar front. They're going to be those areas of low pressure. They're going to start developing and they're going to grow. They're going to get to be bigger, both physically and deeper, as in the pressure is lower. And they're going to go through a whole life cycle. And as they spin in their counterclockwise way, they're going to be dragging that polar front on the west side. They're going to be pushing it farther to the south. That polar front's going to become a cold front as you drag that cold air down to the south. And on the east side, they're going to be, the counterclockwise rotation means that you're dragging warm air to the north, and that's going to be a warm front. They're going to have all this nifty story to them. Before we get there, hey, dry lines. Our fourth type of front, we didn't dwell on it too much. You know why? Because the main awesome part of dry lines is that they're connected to tornadic outbreaks, right? Tornado Alley is where it is, and through Texas and Oklahoma and Kansas, because they get a lot of dry line type fronts there. Okay, where you have cold air, you have dry air on one side, warm air on the other. You watched a crummy 8-minute video that explained why one side was more dense and one was the other. Do you suppose that's going to be on the test? Absolutely. Okay. You guys took a quiz about that, and almost everybody got 100% on that quiz. Look at those questions again. Make sure you can answer them, etc. Okay. You guys do good. Going back, cyclones. Cyclones are going to have that whole story of their life cycle, where they were moving along that polar front, and as they did, they started off as just a weak little area of low pressure. They got stronger and stronger, and their circulations got stronger and stronger, and they started kicking that cold front to the south and east, and they started dragging that warm front north, and they were moving that cold front way faster than the warm front, which meant eventually the cold front was going to catch up with the warm front. That's the nature of things that are going faster than things that go slower. Sometimes you say things that you can't even believe you said in your class. And the nature of things that are going faster is that they catch up to things going slower. Then that cold front, when it catches up with the warm front, becomes an occluded front. Now, let me let you off the hook on something. So for the folks who actually bother doing the readings, God bless you, you might notice that your book then goes off into crazy territory and starts talking about multiple different types of occluded fronts. It talks about cold occlusions and cool occlusions and warm occlusions. I forget how many different types of occluded fronts there are. Do not care. I don't care, and command form, you don't care. Do not care. Okay, I'm not going to ask you about cold occlusions and warm occlusions and, yeah, no. Okay, occluded fronts are enough of a pain in the butt in the sense that they're hard to find anyway. Not that they aren't common, the problem is there's not much difference between the two sides of the front. Both sides of the front are now cool air masses. Maybe one's a little colder than the other or something like that. Maybe one's a little more humid than the other. But by and large, they're just kind of the losers of the front world, okay? They don't do very much. They are the beginning of the end of the cyclone. Because they don't have much temperature difference from one side to the other. So therefore, they don't have much of a thermal wind thing going on, which means there's no jet stream on top of them anymore. And that's going to be part of the whole story of cyclogenesis and cyclolysis. Cyclolysis happening now where the cyclone is dying. Without that jet stream on top of it, and its upper level divergence, and it's, oh my God, positive vorticity infection, please tell me, Dr. Shruggy, that is down on the test. Wahaha, yes it is. But we're not there yet. That occluded front, though, it's kind of a loser. It doesn't have much going on in it. The two sides are so similar, who cares? Man, that boundary, that polar front, is such an interesting place. You know, and some of those early diagrams we had, it was just a line. And the anatomy of the general circulation handout that I gave you the first day, you can download from the files section in Blue Line 2. You can see that I just drew a purple line on the ground. Okay? It's nothing like that at all. It's this dynamic fluid boundary where little cyclones are spinning up, going through their life cycle and dying, and as they do, they're throwing cold air south and dragging warm air north. Cool. Families. I love that anthropomorphization. Anthropomorphization, whatever the right word is. Where we think of them as being families of cyclones, where along the polar front, all around the world, at any given time, you can find maybe 5, 6 cyclones going through different stages of their life cycle. Some are first developing and experiencing cyclogenesis, others are mature, others are dying. It's like a family. It's such a happy term. Oh God. Then we got that business on Wednesday. That whole story about cyclogenesis and cyclolysis. Why were those cyclones developing on there? Because before that I had just invoked the proud Jesuit tradition of faith. I had said to have faith. Cyclones will form along this front. And you diligently wrote it down. Or didn't. Now we started figuring out why. And it was a very complicated story. We have things like narrated PowerPoints that show it, by the way. Again, if somebody wants me, just remind me and I will post it. I just, I got a million things on my mind after the class. I never think of things like that. Okay, but I have things like that from previous semesters. We can show it. But here was the story, remember? We have a polar front. Cold air on one side, warm air on the other. And by the thermal wind relationship, we knew there was a jet stream sitting on top of it. It was such a miracle to me. Cold air and warm air at the surface causing a jet stream kilometers up from there. It's astonishing. And that jet stream, oh sure, sometimes it's zonal, to throw a vocabulary word around. Sometimes the jet stream just flows straight from west to east. That's boring. Nothing goes on in the meteorology when it happens. Most of the time, though, the jet stream becomes meridional, where it meanders from north to south as it goes from west to east. And that's cool, because then we had the troughs and ridges. Remember troughs and ridges in the jet stream? So, for example, here we have a stationary front, just a boring old stationary front sitting here, with a mid-latitude jet streams hanging out on top of it. Notice I didn't draw the whole thing. I'm not caring about what's going on in the western United States. Let's just care about this piece right here. We've got a jet stream hanging out right on top of that polar front. The polar front's at the surface, the jet stream is aloft. And that jet stream has troughs and ridges. Come back here, buddy. There. Has a troughs and ridges. Here's a trough. Remember, a trough is a region where the jet stream was headed to the south, then makes a left turn and starts heading back to the north. A ridge, by the way, was the place where the jet stream was headed to the north, and then makes a right turn to start heading back to the south. You have this trough there. Troughs have vorticity, and ridges have vorticity. Troughs have positive vorticity because the flow is turning in a counterclockwise way. Ridges have the negative vorticity because they're turning in a clockwise way, and this area between the trough and the ridges, which is where the action is where the flow has neither positive nor negative vorticity, but has positive vorticity advection. And this is about the point where in Wednesday's lecture people started getting lost. Positive vorticity advection is in that area where there's no vorticity. The flow itself is straight, but the air that's coming towards it has positive vorticity. Advection is moving stuff with the wind. Most of the time we move something a lot easier to think about, like moisture or heat. But here we're moving positive vorticity. Oh, that makes my head hurt. Positive vorticity down here in the trough, no vorticity here, but the air that's coming towards here has positive vorticity. That means this area is experiencing positive vorticity advection. It's expecting a package of positive vorticity. And what that really means is that air has to lose its vorticity. If that air that is shooting through that trough right now and has all this vorticity keeps it, it's not going to make this straightaway. It's going to be like a NASCAR driver that just keeps turning the same direction. He's going to turn, he's just going to go in a big circle. If he's going to make it through this jet stream and stay in here, he has to lose the spin. Losing spin. We talked about that on Wednesday. When a figure skater loses spin, the way he does it is he puts his arms out. He spreads out his arms, and that makes him lose spin. It's a conservation of angular momentum thing. Whatever. In meteorology, we don't use the word spread out. We say divergence. This air parcel that is shooting through this trough, to lose that vorticity so he can make the straightaway here, has to have divergence. The air has to spread out. And what does that mean at the surface underneath there? At the surface underneath there, that means that there is less air above you than there was before. If you get nothing else out of that whole cyclogenesis thing, it will be useful for you on the test. I'm not telling you that that's a question on the test or anything like that. I'm saying it will help you answer questions on the test, to understand that areas of positive vorticity advection have divergence aloft. Up near the tropopause, it's experiencing this divergence. At the surface, there's now less air above me than there was before. Pressure is just the weight of the air above you. So there's less air above you than there was before. Apparently your pressure is going down. We are giving birth to a cyclone here. Push, push. I get no sleep anymore. I have an infant. I think of all these analogies about babies. Cyclogenesis, the birth of a cyclone. We have created, just by the fact, think about how astonishing this is. And the atmosphere is a complicated place. Here's the stationary front. One of the biggest losers in meteorology. Not much going on, right? Colder on one side, warmer on the other. These sides pushing each other out. What could possibly be happening here? Actually, amazing stuff. Because it's a polar front, it's got a jet stream above it. That jet stream's got troughs and ridges in it. That jet stream, therefore, has areas of positive and negative vorticity, which means there's areas that don't have vorticity now, but it's coming. Which means those are areas where vorticity has to be shed, to use the great word. The way it does it is by upper level divergence. Which means on that surface, all of that boring little who gives a damn stationary front, suddenly pressures start falling. Now we have a cyclone. It's going to start going by all the forces you learned in the second unit of the course. It's going to have pressure gradient forces and Coriolis forces. It's going to start developing that counterclockwise rotation. And it's going to start going through its nifty little life cycle. It's going to be an open wave. Throwing vocabulary words around here. It's going to have a warm sector. If we looked at it on a satellite picture, it would be a comma cloud. Ah, man, I am just flinging words off that review sheet like crazy. And at some point, it's going to become an occluded cyclone, because it'll have an occluded front. Oh, I probably should have been walking my way through other diagrams. Here's my positive vorticity advection. Here's my positive vorticity, my zero vorticity, so this is the area of positive vorticity advection. You can get all these. I have the link to this outline on that inventory of resources that are available to you. You get that upper level divergence in the area of positive vorticity advection because you now know, if you know nothing else, positive vorticity advection aloft means divergence aloft. And then that gives you an area of low pressure there at the surface. Starts rotating, your stationary front ain't so stationary anymore. But a couple of days later, things get bad. That cold front starts catching up with the warm front and making that occluded front. Make sure you know how to draw an occluded front. You know, it's got the triangular teeth and the semicircular teeth on the same side of the line. All of you say, well, what a loser. I mean, this is the cold front air mass. This is a cold air mass. The only warm air is down here. This front isn't really doing much of anything. It's not really all that different than the two sides. Thermal wind relationship says, I ain't putting no jet stream on top of that. And the jet stream moves to be up on top of these polar fronts, and you end up with a low that is sitting there with no jet stream on top of it, no vorticity advection on top of it, no upper level divergence on top of it. Why would there be low pressure there anymore? Well, there wouldn't be. The low pressure is going to start experiencing cyclolysis, lysis being a suffix that means death. What does a cyclolysis mean for a cyclone? It means that its pressure's low, but it's getting higher all the time. It's headed back towards normal. You know what? That occluded front's hard to find. If you look at weather observations, it's hard to find when there's so little difference between the two sides. That low pressure is every hour it's getting closer and closer to normal. Before long, you can't find the thing on the map. And it's gone through its little life cycle. It's not pretty, but it's the way. It's nature's way. It's born, it lives, it dies. And it's all happening along that static little picture that we saw at the beginning of the day. At the beginning of the lecture, when we were looking at, let's say this one. I mean, who would have guessed that so many cool things were just happening along this little front right here? And who would have guessed, I mean, the diagram didn't even bother showing that these jet streams are here, and how they have troughs and ridges in them, and the troughs and ridges change from day to day as they try to stay above the polar front. And all the other cool things are going on top of here. And I think the rest of these little diagrams here about cold fronts and stuff, they aren't so useful. There was one other topic, one little module we slipped in. Satellite meteorology. You might have figured out at this class already, we have a number of little modules that are like 10, 15 minutes long that we can sneak in when we need to. I know I want to show you satellite pictures of something, so first you need to know how satellite pictures work. Okay, we can slip them in when we have a chance. Same thing's going to happen in the next unit. When we start doing severe weather, when we're going to start looking at radar plots, I got to slip in and think about radar at some point. Okay, the PowerPoint that we did about satellite meteorology is, of course, on Blue Line 2 under Files, and you can get it. Remember, satellites can do all kinds of cool things. They can do things like measure the speeds of the winds. Well, remotely. It's a type of remote sensing. But they can detect things like pressures. Well, pressures are hard. Winds, humidity, temperatures, etc. But the main thing that we care about in this class is the fact that they just have cameras on board that can take pictures. And there were two different types of orbits that these satellites could be in. There were those geostationary orbits that are way the hell out there. 36,000 kilometers or something like that. They're way far back. This is taking the broad view. From way far out there, the satellite could basically see half the Earth at any given time, right? They see a full disk of the Earth, which is pretty cool. And there's a reason why they go into that orbit. It takes 24 hours for a satellite in that orbit to go around the axis of the Earth, during which time the Earth turns 24 hours. So from the point of view on the ground, it looks like the satellite's not moving, because it's all just turning at the same rate we're turning, which is pretty darn useful, because from the point of view of the satellite, then it looks like it sees the same view all the time. Very handy. Unlike those polar orbiting satellites. Polar orbiting satellites are in a really, really low orbit, like 300 kilometers. And they go up over the North Pole, down over the South Pole, up over the North Pole, down over the South Pole, and they're really, really fast, like 18,000 miles an hour or something crazy like that. But they're so low, they're effectively like high altitude aircraft. They can only see a little area underneath them, relatively little area underneath them at any given time. Boy, they can get some high resolution pictures when you're only like 300 kilometers above the ground. On the other hand, they're never where you need them. Right? If there's a particular storm you want to see right now, the likelihood that there's a polar orbiting satellite shooting right over it right now is not so great. Because, I mean, they can only see a little area of the Earth at any given time. So those are mostly used for research purposes. The kind of satellite pictures you saw on TV were always geostationary. Now, well, sorry, we're taking my satellites in geostationary orbit. Now, the satellite itself on board has two different kinds of cameras. One was the visible cameras, which were taking pictures basically what your eye would see. Well, in black and white. But like, for example, they only work during the day. Because, you know, it's dark. They see things like shadows on the ground, high clouds casting shadows on low ground. They're also really high resolution. Those visible pictures are really very high resolution. But they don't do crap for you at night. But what works 24 hours a day were those infrared pictures. Infrared images are really taking a measurement of the temperature. They're using Stefan Boltzmann's law. Oh my God, we're throwing a term from the first unit around. Because remember, the amount of radiation that comes from an object depends on its temperature. So if they see a lot of radiation coming from here and not a lot of radiation coming from here, they can say that place is warm, that place is cold. Well, in the atmosphere, something that's really cold is probably higher up, so that's like a higher cloud. This is a warmer area, it's probably a lower cloud or even the ground. But that works day or night. They can take those pictures day or night. It makes no difference whatsoever. I remember being very confused about that when I was first taking this class many, many years ago. I was like, how the hell do they get those pictures at night? Is there like a big flash bulb up there in the sky? How does this work? No, they're infrared pictures. But infrared pictures don't have very high resolution. You can't see every little puffy cloud. You can see like it's cloudier in this part of the country, it's less cloudy in that one, but you can't actually see like individual clouds on infrared satellite. That's my whole reason that's not satellite meteorology. Man, we covered a lot of material in this unit. And a lot of it's very visual stuff. That's why I gave you guys a big inventory of all that stuff that you need to prepare for the test. The test has been written, and I would describe it as longish. Okay. In its current draft, it is 75 questions, I think, which is a little long. I plan to thin it down over the weekend, okay? You know, because I mean, you only have 50 minutes to take the test. If you need a few more minutes at the end, you guys know, we can go upstairs to the conference room or something like that, because somebody else needs to use this room. But I think 75 is a bit long. I mean, they just sort of keep drawing questions until we've hit all the topics, and I think it got a little long. So I'll probably knock a few of them out of there. But still, it's going to be a longer test. I mean, I'm not going to knock it all the way down to like 50 questions or something like that. That would be not enough. So it's pretty longish, but you know, here's the deal. If you were new to this class and you hadn't seen this material and so on, you wouldn't look at the test and see it like it's anything different. It isn't like this test is 50 pages of color diagrams of the general circulation. Okay? They're word questions, just like everything else. Occasionally there's pictures that have a little sketch or something associated with them, but by and large they look just like the other ones. You have to be able to use your words to describe what you're picturing. Right? A perfectly reasonable question. I think I had one like this on the quiz. Put these features of the general circulation in order from the equator to the pole. polar easterlies, trade winds, polar front, subtropical high. Okay, you have to have the picture in your mind as to how these work, and then you're using words to answer the question. Okay, that tends to be, there's reasons why it's asked that way. Okay, all right. It's going to be a big test. You have a big weekend. I will be able to answer questions via email, whatever. I have lots of office hours on Monday. The help desk is open a lot between now and then. Get the questions answered so that you do well on the test.